slides. So what I would be talking about is what I would give a brief introduction to structural design and how it is, and also to the capacity design. And I will take you through how capacity design is different to a structural normal gravity structural design. And also I will also go through some of the common structural systems we apply in industrial buildings. Here, when I refer to industrial buildings, they are light industrial buildings, not the heavy thermal power plants or petrochemical units. And also I will be touch basing on some of the common structural systems what we use in commercial buildings, right? So as a first module, I would be talking about the structural design and how it is different to capacity design. And right, when we think of structural design, it straight away comes down to the structural components. Say for example, you have a simple portal frame structure. So we talk about how to design a floor, and we talk about how to design a beam, and we talk about how to design a column and as well as foundation, right? When I say what the design, what we mean is basically arriving at a sizes that can withstand the probable loads that can experience during its lifespan. At the same time, you don't experience unintended vibrations or deflections, right? So basically, we divide our structural design basically into two limit states. One is ultimate limit state, which is governed by strength, and we also design for serviceable limit states, right? Where we check for deformations and deflections and vibrations, right? And also this portal frame can be of a different materials. Let's say a concrete or a steel or a timber, right? They all behave very differently. So when it comes to member design of say timber floors or steel floors, it's predominantly mainly governed by deflection. And whereas if you have a steel or timber frames, they are generally governed by strength, right? You have to be careful, right? Timber is a live material. You also need to think of long-term deflections. They govern most of the times. So when it comes to concrete, the concrete floors are generally governed by strength, and also the frames or walls, the main structural systems, they are also governed by strength. You know what? One important aspect of the seismic design is ductility, right? Ductility is nothing but how much it ultimately can deform to the yield deformation capacity. It's nothing but ratio of ultimate to yield capacity or yield displacement capacity, right? You have to keep in mind steel and RC structures can be designed ductile, whereas timber can't be designed as a ductile. It's always a brittle material, right? If we quickly recap our structural member design, let's say from basic undergrad course, let's say if I ask you to design a simply supported beam, so basically, if I ask you to compute the deflection, if I ask to check against the limiting deflection, it's simply 5QL power 4 by 384 EI, right? So which is the actual deflection that would occur in a superimposed dead load. So you need to limit to allowable limit, which is generally stand by 300. So as long as you meet this criteria, you say that the member is not deflecting too much and it satisfies the serviceability criteria. So when it comes to, say, for example, strength design, and you want to design a concrete beam, so what you do is basically you feed factor and you want to design for a flexion, you want to check its flexural capacity against the flexural demand. You simply use this formula. Just keep a note, to make you guys easy. Just follow my mouse cursor wherever I take you, so that it's easy to understand, right? So one thing to continue further, if you want to compute the flexural capacity of say concrete section, it's a quite simple formula, which is area of steel times the lever arm. So which is you represent as JD, which is most of the times 0.85D, right? And also you have to do further checks to make sure the steel to concrete ratio is in 0.3 to 3%. And if your actual demand on those particular concrete element is say less than 0.15%, you simply ignore its contribution. These are simple basic methodology to compute the flexural capacity of your concrete section, right? Similarly, if I ask you to compute the shear capacity of your concrete member, this is well-known formula, right? 0.85 DF by AST by S. where S is the spacing of the stirrups. So again, one thing from the basic fundamentals, if your stirrup spacing is more than 0.85 JD, it's not going to contribute to your shear capacity. At the same time, when you do seismic design for a very high ductile, you ignore the contribution of the concrete to the shear capacity of a section. Similarly, if I ask, how do you compute steel member capacity? It's nothing but yield capacity times section modulus. It could be plastic section modulus. You can, conservatively take elastic section modulus, right? So I take an example where I took a two-bay beam taken from a multi-story building with a cantilever, and it has, say, I compute all the bending moment envelopes if I have to design it, and then with this particular two-bay cantilever, I want to make sure I want to have a real hinge next to the support B. So in that case, I need to make sure in reality also I am achieving the real hinge there. That's how then it's behaving how it should behave, right? So when it comes to normal structural design, what would you do is basically you estimate all the dead loads, live loads, superimposed loads, any other environmental loads, and you arrive at a bending moment envelopes, right? So once you arrive at the bending moment envelopes, which means the maximum moment demand at a particular section. It could be at a support or it could be at the midspan. Once you know those demands, as I said in my previous slide, you can easily size those members. And at the same time, I sized my members. What about my connections? So as I said, I want to have a really hinge here. How I'm going to ensure that? For example, if I'm using a steel section, so I need to make sure there is no real moment transfer, right? That's how then it is behaving how it should behave. Similarly, if I'm designing a timber beam instead of a steel beam, so the connection going to be very different, right? So it depends on what kind of material you are really designing and what kind of a beam. For example, if I have to design a concrete beam for the same problem, so you need to, if it's a cast in situ concrete beam, I want to really achieve that, hinge behavior so that there is no moment transfer. How do you achieve that? By truncating the longitudinal top and bottom bars and introducing a coupling bars which are diagonal shear bars so that they just transfer the shear but they don't transfer the moment, right? And these are the basics. And say if instead of a cast in situ concrete beam, if we have a precast concrete beam, how do we achieve the real hinge connection there? We create a kind of a rebate and we seat the small beam on top of it, and there is no really a continuous connection. So what I'm trying to tell from this is, once you size members, you need to also size your connections so they behave exactly how they should behave, right? Similarly, for example, if I have to design my shear reinforcement, I get my shear envelope, right? Once I have my shear envelope, I can size my spacing of stirrups. And one thing, as we know that the shear demand at the support is going to be large, so obviously shear spacing going to be very close at the supports, right? As you go to the center of the beam, so the shear demand is almost zero. So, and you provide a nominal shear reinforcement to make sure constructability and also to make sure any shift in the point of counterflexure. So also, right, this is a basic structural design. So this so far what I talked is about the member design, right? Now it comes to the connection, right? So which is the one which transfers the forces from the members, between the members, say from the beam to column to foundation. As long as you have a intended connection, it transfers intended demands. So if you mess it up with your connection, then there possibility of unintended force transfers. So for example, in this case, you have a one-way portal frame there, and the connections we need to really take care of is the base to foundation connection and also beam to column connection. So which means you need to really closely look at what's happening in that connection region. You need to think about the stresses, strains, and also you need to make sure you detail such that it transfers the intended forces from one element to another element, right? Again, the connections, it could be a concrete connection, it could be a steel connection, or it could be a timber connection. So that adds more variety to our structural engineering problems, and they completely behave, and the design is different and detailing is different, right? So when it comes to connection, you classify connection based on its stiffness and strength, right? If a connection is really stiff, which means really rigid, so which means you have a continuous load, compatibility, not load path. For example, you have a 2-story one-way, frame here with a continuous connection. So because of this continuous rigid connection, you're going to end up having a double curvature bending. For example, if the same connection, if it is a pin connection, you're going to have a cantilever behavior in your columns, right? And so what I'm trying to tell you is, depending on your connection stiffness, the overall deformation behavior is completely different. So you need to really take care of in your design and your modeling. Let's say, for example, to make it even further simple, you have a simply supported beam with rotational springs at both ends. If your springs are really stiff, which means it's a fixed condition, which is shown as a red dotted line, and the demand is going to be WL squared by 2/1, right? So, and obviously, if the spring stiffness is almost zero, then you are changing from a fixed condition to pin support, which means you're not going to have any demand at the ends, and your central demand going to be WL squared by 8 for a UDL case. So, so what I'm trying to tell from this is, you need to take care of connection stiffness when you design and your model as well. And the next important topic, what it also matters, is the connection strength. For example, if your connection is if your connection is brittle and greater than the member strength, it's fine. Whereas if your connection is weaker and brittle than the member strength, then you are asking for a trouble, which is not really required from a seismic engineering point of view. That's where it leads to capacity design. So where we specifically design such that we have a flexural yielding mechanism in the members, and we avoid any kind of a brittle mechanism, right? So to make much easier to understand, let's go back to basics. Let's imagine a chain, right? You got a multiple brittle links and you got one ductile link. If we assume our structure as a, if we assume our structure idealized as a chain, the chain will have both ductile and brittle elements, right? To ensure ductile failure, we must ensure ductile link yields before the brittle links. Otherwise, brittle will fail, right? So, what the weakest link dictates the chain behavior, right? Strength of the whole chain is the strength of the weakest link. Similarly, ductility of the whole chain is the ductility of the weakest link. So in this, bottom picture where you can see, the brittle links, they're not going to yield, whereas the ductile link stretches, and that governs the whole behavior of your entire chain, right? So to make it even, easier for the viewers, let's assume that you got one ductile link represented as D in blue color, and you got one, say, brittle links represented as, B in a red color. I have a chain of 3 links where the first link got a capacity of 1 kilonewton, and the brittle links got a capacity of 1.2 and 1.01. One thing, if you look in the load deformation curve here, obviously because it's a ductile link, it got a deformation capacity, whereas the brittle link, it doesn't have a deformation capacity. It's gonna fail all of a sudden. So if I club all the behavior of this, case A, you're gonna have an overall ductile mechanism because ductile link is weaker one. Say by any chance, if we increase the strength of the ductile link, say to 1.02, then your brittle link will govern the overall system behavior. So what it means is, increasing element strength does not increase its overall performance. Strength hierarchy rather than absolute strength is important. Brittle link should be designed based on capacity of ductile lengths. So that's what I want to tell from this. So if you look the load deformation, plots, what you see on your right bottom most. So you got a weak link, which is ductile, and it got a low capacity, then a strong link, which is brittle. So overall, you're going to have a ductile mechanism. Similarly, you got a weak link, which is brittle, and you got a strong link, which is ductile. So in that case, your overall system or a chain behavior gonna be very brittle, which we don't want in a seismic design, right? How do we apply the capacity design, whatever I said so far, to a real structures? Let's have a brace frame design here. Say I am designing a particular brace component, right? I want to make sure my brace is relatively ductile, so which got a continuous low deformation, and also I want to make sure my connection, it could be welded or bolted, to be if it is a brittle, it has to be stronger than my brace. So what it means is I must make my connection stronger than the brace strength to have a ductile tensile yield. So if I apply a same capacity design principle to say RC column, right? I know my flexural yielding behavior is relatively ductile if I weld detail it, so which is going to have a good load path, and you can see what would be a ductile flexural failure in a real column would look like. And say generally shear failure is very brittle, so you would see the mode of failure what you would encounter in a real shear failure scenario. So what it means is, in any case, I should avoid shear failure, and I should make sure I have a nice flexural yielding in my RC column or a beam, right? That's the whole idea behind it. So now it comes to a question, who has to fail first and how? So that's where your strength hierarchy comes into play. So based on consequence of their failure, let's say you take a multi-story RC frame building, where you have a slab. If slab fails, only a particular room gonna get affected. For example, if a beam gets failed, a particular story gonna get affected. And if a column fails, it's gonna affect the entire building. And say if foundation fails, it's even more serious. And if soil fails, your structure is it's standing there, but it's no use, and it might collapse, right? So you need to work on your strength hierarchy and also your load path. So what it means is failing elements need to be ductile, right? For example, you have a RC moment resisting frame with the infill brick wall. So you need to make sure your beam hinges so that you're gonna achieve a relatively ductile performance rather than a column story hinges or a soft story mechanism, they call it, which is a non-ductile collapse like what you see in the bottom. So we don't want to have that kind of a design. We want to make sure even if your building deforms, it stays there so that people can evacuate from the building, right? So that's from the system. If you come back to the element level, for example, you are looking at say beam element. As I said, flexural failure is always it's a good ductile yielding, which is predominantly you see a vertical kind of cracks on the beam ends, which we call it as a plastic hinge region. So when we design in a capacity design, we make sure we achieve a ductile mechanism. So before it reach, the brittle elements reach their capacity. So what we're trying to make sure is there is, we're trying to achieve this blue line in our design, not this red line. So if for any chance, if you have a shear failure, you're going to end up having a very catastrophic collapse, right? That's what we observed in real earthquakes. Now, when it comes to a frame building, so it comes down to whether we need to design a strong column, big beam, or a big beam, strong column, right? Always the desired fundamentals tells us that you need to design big beam and strong column so that your beam hinges and your building stays there. But other way, if you design weak column and a strong beam, your column gonna collapse and your beam is intact, which means your entire building gonna turn into mechanism and it's gonna collapse. having said that, if you have a 2-story or 1-story, if you have a good ductility in your column, sometimes we do allow weak column to strong beam design, right? So how does it really look like a flexural failure of a beam? It's basically the bottom face stretches, and you're gonna have a permanent deformation. So whereas if you look into a shear failure, it's gonna be all of a sudden. So you're gonna end up having an inclined crack very close to the support, because that's where your demand's gonna be high. So which we don't want to have in our seismic design. Let's look at, for example, the same building which got subjected to a couple of cyclic shaking. So what the damage pattern, what you see in a flexural behavior is what you see on the top figure here. And also if you have a shear failure, you're going to have a diagonal shear cracks which will lead to immediate collapse, which we need to avoid most of the in any time, right? So what the conclusion from this is, we need to have a flexural failure before any shear failure happens. And the failure modes, if I have to summarize in an RC element, is gonna be, you're gonna have a bond failure, which is a brittle failure, which we should avoid. And in modern codes, we avoid bond failure by providing enough anchorage length and by providing deformed bars. This is a problem of old structures, so we don't need to really worry about it now. And the other mode of failure, what I was talking about, is the brittle mode of failure, right? And the other mode of failure is a flexural failure mode, which if your beam is over reinforced, you might have a brittle compression failure, which we need to avoid it. So the other desirable mode of failure is always under reinforced beam, where you got a yielding in your bars before compression strain is reached in the top compression concrete. So that's the green what we intending to achieve. So hence ensure bond failure doesn't take place, shear failure doesn't precede flexural yielding, and beam is always under reinforced. So if I have to list steps what we follow in our capacity design, first step, assess required strength of a chain, which is structure from seismic code, apply suitable load factors to calculate design demand. And the second step is identify desirable collapse mechanism and the weakest element mechanism, which is a beam mechanism, right? Step 3, design the ductile element, in this case beam, to have enough strength to meet the demand, and apply suitable safety factors to the material properties, right? And step 4, assess the upper bound strength, that's we call as O strength of the ductile element, right? We call it as a O strength factor. Now design the brittle elements to resist the loads corresponding to the O strength of ductile element. I will explain you in a minute what it means is, and ensure finally the ductile element has enough ductility through appropriate detailing. If you don't design with appropriate detailing, it's not going to behave what you want to, right? If I have to put whatever these steps into simple equations, one thing is design strength of the brittle elements need to be more than O strength capacity of the ductile element, right? O strength factor may be multiplied by dynamic magnification factor if we have to include higher mode effects. This is only applicable to very tall structures, right? So from design point of view, what is the design strength? Nominal strength times strength reduction factor, which is always less than 1. For a flexural, it is 0.85. If you are doing in a shear, it is P factor is 0.75. And O strength, what is a O strength? Nominal strength times O strength factor, which is always greater than 1. So generally, O strength factor for reinforced concrete elements is 1.2. It's basically to account for strain hardening effects and to account for lower characteristic strength of yield point of a steel, right? And also you need to think of the actual strength of your any component or structure is going to be a lot higher than what you designed for, basically because of safety factors we apply in our design, and also the load factors we apply in our and also the load factors, and also sometimes we provide the reinforcement more than what it should be required, and also confinement increases, the strength of the members, and strength contribution from non-structural elements, and special ductile detailing adds to the strength and redundancy of the structure as well. These are all, we don't really address them directly, but these are all add to the strength of your overall structure, right? So if I apply the capacity design, whatever I spoke so far, to real structures, let's say if I have to design a welded steel connection, right? The desired behavior is I need to have a yielding spread over long region in the beam, which is a yielding. What undesired behavior, I don't want yielding concentrated in a discrete weld region, because I know welding is weld failure is a brittle failure. That's what we observed in the Northridge earthquake in 1994, where many buildings got collapsed because of weld failure. So the capacity, if we apply a capacity design, so weld must be stronger than beam. That means weld is a brittle link and beam is a ductile link. So the final equation comes to this: design strength of the weld has to be more than the overall strength of the beam, right? Similarly, if I apply capacity design to reinforced concrete bridge pier, right? The desired failure mechanism is flexural yielding. Undesired is shear failure. That's what I've been talking about. If I apply capacity design, I need to ensure flexural yielding before exceeding the shear strength. So which means desired shear strength has to be more than the overall strength flexural capacity, right? For example, I need to design this bridge pier for say 500 kilonewtons of force, but due to the available bar size and strength reduction factor, I provided nominal strength which is higher, and say let's assume it's 600 kilonewtons. So if I assume overall strength factor of 1.25, then the design strength has to be shear strength. I mean the spacing of the stirrups and hooks and all need to be designed for 750 kilonewtons, not to the shear demand of 500 kilonewtons. That's the whole crux of capacity design. You are amplifying the demands for brittle modes of failure, right? So if I apply a capacity design for a frame, so the left figure, what it shows is a beam sway mechanism, where you put links in your beams, hinges in your beams, whereas undesired mode of failure is the column sway mechanism, right? To prevent the soft story mechanism, we must prevent plastic hinging to happen at top of the first story, right? So how do we do that? Say let's zoom this corner point where you got a column and you got a beam. This is gonna be the bending envelope, right? So we know from equilibrium, the top moment in the column and the bottom moment in the column would equate to the beam moment capacity, right? Which means, and also you need to make sure column moment may increase due to beam overall strength factor. Hi, can you stop it for a while? Can you stop it for a while? Can you do something else, please? If you're done, just stop it for a while. Yeah, please. Yeah. Oh, sorry. I mean, there was cleaning going on in my office. Anyway, yeah, let's go back here. What I was trying to tell is, right, if you look into the equilibrium here, the column moment in the top column moment plus the bottom column moment in the column would equate to the beam moment capacity, right? But the column moment can be increased to beam over strength and also to the dynamic magnification, which is due to higher modes, which is a higher topic, but let's not go there now. So what we are trying to do is we're going to increase the column capacity by applying those two factors, and so that we avoid any kind of hinging. So let's go and see how we do for a say moment resisting frame, right? So what we are trying to achieve? So we are trying to achieve column flexural strength is more than maximum likely flexural strength of beam plastic hinges, right? And also we are trying to avoid shear failure, which means we are trying to do shear capacity of that member is more than corresponding shear force that would arrive due to beam flexural overstrength, right? One big problem or uncertain thing is how do we really assess maximum likely flexural strength of beam plastic hinges, which are shown as these dots. The plastic hinges is nothing but damaging, right? It's an important issue in seismic design of RC frames, right? And like for example, if you have this frame which is subjected to lateral loads and you want to have a beam hinging, which is a ductile mechanism, and that's what the intending mechanism in a good seismic design philosophy. And for that, what you need to make sure is basically you avoid any shear failure in the beams, and also you avoid hinging in your columns apart from at the base. You can't eliminate the hinging at the base, which still is a stable mechanism, right? So how do you design the shear in the beam so that you avoid shear failure? One thing, you assume both ends of the beam is have a plastic hinges, and the corresponding overstrength moments is say MOA and MOB, right? That's purely due to earthquake demands, right? And you got on top of it gravity load, say W. So the shear demand is gonna be WL by 2, and you're gonna be and the shear demand due to earthquake load is gonna be overstrength moment demand at both ends divided by L. That gives you your shear demand. Once you make sure that you design for it, so you are avoiding shear failure in your beam. Similarly, you need to also design your column such that there is no plastic hinging, right? How do we do that? So you take a sub-assembly of that component and you apply overstrength moment demands that what you get from the beam, and then you take a equilibrium of that column element, and which means the column capacity what should be more than beam or overstrength hinge moment, so that you achieve equilibrium in the beam column subassembly joint, right? So in the same way, you also need to avoid shear failure in your column. How do you do that? So basically you take equilibrium of the subassembly where you sum up the overstrength moment demands on your beam on left side and right side and divide by the story height, so which would give you shear demand. Once you make sure your shear capacity is more than the shear demand, you are obviously eliminating your shear failure. That comes to the first part of the presentation. Now what I'm gonna do is I'm gonna quickly take you through some of the common structural forms and connections what we see in industrial buildings. This is mostly covering in New Zealand, but nevertheless if the same applies to even structures in India as well. So right, the overview of this module is basically gonna be a bit of overview and steel industrial buildings and timber industrial buildings. Timber is very common in New Zealand, as New Zealand produces a lot of timber, and it's treated as a structural material rather than just a carpentry material, right? Industrial buildings in New Zealand are mainly constructed in steel and timber. They usually adopt long span portals. They can span between 20 to 70 meters in one direction, and spacing of the frames can be between 5 to 10 meters. The portal frames are designed for vertical and lateral loads, and girts and purlins and bracing elements to pick the roof cladding, right? The static scheme of the portal frame can be hinged or full fixed connections at the bottom, and the static scheme in the long direction of the building is typically hinge changed. So we need a lateral bracing so the system is stable, right? So you can see typically the kind of steel industrial buildings what you would see here. The first one is a cold form steel structure, and the second one what you see is hot rolled steel sections, and even you see on the third picture what you see is again cold form section, and the fourth one is again hot rolled steel portal frame section, right? So the connections, when it comes to connections, so you can see kind of a closed clip connection for apex bracket for a cold form portal frame section, and you got a haunch or knee bracket section and connection detail for a rafter to post connection. And the connections for a hot roll sections can be a bolted end plate connection like what you see on the left bottommost figure. And sometimes these connections can be welded so that the column and little stub comes as one piece. So we introduce a little splice to make construction a bit easier, right? So as I said, these portals frames, they need braces in the roof to transfer the roof initial loads to the foundation, and also they need a wall bracings. So these braces are generally either steel hot roll sections, generally mostly angle sections, and they are also tension rods sometimes, most of the times, not sometimes. So basically the rods, they just take the tension load and the compression is redistributed to another way where it transferred as again tension load. The column to foundation connections can be either fully fixed connection by using end plate with stiffness and J bolts kind of stuff, and the base connection sometimes they are pin connections as well. So which means you provide your bolts on neutral axis so that you don't achieve any moment capacity, right? So this is interesting. We also have a timber industrial structures where we use extensively timber portal frames for commercial complexes, industrial buildings, and also even large warehouses, right? How do we design it? So again, to the shape of the rafter and post, they generally follow the bending moment diagram, and to achieve and sometimes we provide hinges like 3 hinges at the knee location, at the apex and the bases. So how do we achieve a moment connection at the rafter and at the junction of the rafter and what you call the post? We use generally in the radial kind of bolts or screws that enables to have a continuous rigid connection. Also, to achieve pin connection, we have different kind of steel connections which are just able to transfer the shear. And also one thing we do is we don't really connect timber straight to the concrete, to avoid timber rotting, right? And also sometimes we use timber hinges, steel timber hinges, where we encase the steel end plates with real hinge, and also we screw the steel plate to the timber. And also we have a real steel hinges at the center of the apex with what you see here. There are different endless options what you can experiment. So if you want to have a continuous moment connection, then what we do is we stick a plate on top of it and screw the nails. And there is a methodology how you can calculate how much moment it can carry. And also you can sometimes screw the plywood, and we like what you see in figure C here. Sometimes we have exposed double bars which can transfer moment from the rafter to the post, right? Sometimes we use hybrid steel to timber connections where you got beams are timber, whereas your columns are steel columns, right? So if you look back, so that's a kind of a overview I want to give for industrial structures with timber and steel. We don't have a concrete industrial structures much, as it is uneconomical. And also now coming back to the structural forms and connections in commercial buildings. Again, I just want to give a overview with what are the common structural systems we have in steel buildings and concrete buildings and timber buildings, right? So multi-story buildings in New Zealand are predominantly constructed using steel and concrete, but these days we do have a timber growing quickly, and the lateral loading systems are mainly walls or brace systems or frames, right? and as like unlike US or Europe, New Zealand is not a tall building country. The maximum building height is like 160 meters. That's couple of them in Auckland region. So when it comes to as you all know that the lateral loading behavior of wall is completely different to a brace and to a rigid frame, and sometimes we have a dual system which is of moment resisting frames and walls as well. So mostly the low medium rise buildings use shear frames like what we see in type 1, which is the moment resisting frames, and also we use braces, which is the type 2 ones, which are quite stiff, right? Now, if I want to quickly run through some of the examples with the steel commercial buildings. The first one, what you see is a steel moment resisting frame here, which is I think maybe 5 to 6 stories one, which got all moment resisting connections. And also you got say another building where you got a multi-story building with the K braces, right? And also sometimes we got a if the structure is really high, you got a external diagonal bracing kind of a system. These are all conventional systems. I don't want to go into next generation building systems in this presentation, like base isolation or low damage systems, because that's it's a very advanced topic. And like if you go into basic steel commercial buildings, the beam to beam connections, generally we do need a secondary beams because the floor cannot span between primary beams, which are like they span generally at 10-meter grids. So we introduce a secondary beams. The secondary beams are generally located at the center of the bed, so that the flooring, which is a corrugated slab, generally flush with the top of the steel bed, right? And you can see the real picture how it really looks like, right? And also the beam to beam connections are generally hinge connections because we don't want to transfer the moment. And this can be achieved using standard end plate connections, or it could be a pin plate connection, or it could be welded connection to the web to web, or it could be a connection using a double angle, or it could be just a straight away bolted to the web, right? One thing as an engineer we need to be careful is when we have an offset beam connections, there is a possibility of eccentric moments. When we design those connections, we need to be very careful that any additional eccentric demands are taken care in your design, right? There are different options for connecting primary to secondary beams. The secondary beam can be positioned at the same level of the primary beam and a slab sitting on top of it, or if there are architectural constraints, then the secondary beam can be connected to the primary beam at the lower position, right? Now it comes down to primary beam to column connections. They are predominantly rigid joints in a moment resisting frame, which are achieved through full weld butt weld connections, or it could be full strength moment end plate connection like what you see here, or it could be T flange and pin plate connection what you see on figure F. So there are many ways we can achieve rigid joint connection, right? And also if you have a brace structure, the beam to column connection doesn't need to be a rigid connection because your load is transferred as an axial force into columns and braces. So the connections can be simply hinge connections, which are which could be a fin plate connection or an angle connection, or it could be a flushed moment end plate connection with bolts predominantly at the center of the web, right? Also, the column to foundation connections, they can be full fixed connections, like they are very much similar to industrial structures, right? With end plate and stiffness and with the J bolts, or it could be with doubled anchors as well. And also one thing we need to make sure is they have enough development length, so that you achieve a full fixity. As I talked in my first few slides, connection stiffness and strength can really alter the behavior of your whole system, right? When it comes to concrete buildings, majority of the concrete buildings are precast concrete buildings, where you have a precast elements and they are joined using cast in situ elements, right? So now you can see on your left picture where you have a precast beam with a central portion which is a cast in situ joint, right? And finally what you see is a complete monolithic joint, right? Which got a system performance same as a cast in situ element. The advantage with this is you don't need a formwork. It's a very quite fast construction, and and so these are most of the times in New Zealand, it's the concrete is always precast. There's nothing like on site. Everything comes from the fabrication yard. You simply erect it, and you join either using cast in situ joints or steel connections. Right? There are many techniques how you join your precast elements. The cast in situ joint can be at the beam column location, like what my cursor is pointing towards, or it could be at the center of the beam, or it could be using a steel plate and bolted joints. There are many different varieties how you can achieve monolithic system using precast elements. And timber is getting quite popular in commercial buildings. The timber can be a precast wall, sorry, not precast, timber walls, which could be connected using brackets, or they can be using post tension rods as well, right? And also the timber is also quite common in moment resisting frames. They are using in moment resisting timber frames, where you got a couple of steel connections which transfer the forces from the timber beam to timber column. And there are different varieties how you can transfer the force from beam to columns, right? There's some of the real examples here where the timber beam is transferred to timber column using a steel joint with a kind of a damper here. This is a bit of advanced system. So what happens in reality is when earthquake hits, this damper fails, and so you can replace that particular damper rather than replacing whole building system. This comes under next generation building system, right? And also there are if needed there are many different possible ways how you can connect secondary timber beam to main timber beam using nails and dowels and steel angles and T junction plates and L brackets, or it could be simply endless possible ways how you can connect the timber beam to timber beam, right? With that, I want to quickly recap. Member design can be done need to be done for different limit states, and you need to make sure it satisfies strength criteria and also deflection criteria, and you need to make sure the system make sure capacity is more than demand, and also deflections are within allowable limits. And if you have a connection regions, most of the times your Euler-Bernoulli theorem is not going to work. You might have to use Stratton type principle, which I haven't talked, but so you need to make sure the connection behaves as it should be, right? And also connection is very important in your structural system, as it transfers loads from one element to another element, and its stiffness and strength can really alter your overall system behavior. And coming from there, I talked about capacity design, where we avoid the brittle failure by making sure desired yielding mechanism is achieved and allowing desired flexural yielding in your beams, right? And with the capacity design, what you are trying to achieve is a strong column to big beam, which is a best practice for a moment resisting frames. And I also quickly gone through some of the common industrial structural systems, what we construct in New Zealand with steel and timber, and what possible kind of connections you can have at apex or rafter to post or post to foundation connection. Similarly, what forms of commercial buildings we practice in New Zealand. Yeah, hope with that I concluded. Yeah, I'm happy to take if there are any questions.
Yeah, I request Dr. Ramna from VTU to take over session with question answers, sir. And I request all participants to put in chat box. Ramna sir, over to you.
I'm sorry, there's a lot of cleaning going in my office, so which I didn't really, thought of it.
To start with, so what is the age of timber structure? One
Age?
question. Yeah.
What do you mean by age?
Yeah, it's from Mr.
No. The age of the timber, age of the the timber has to
structure.
timber has to be a treated section because timber shrinks a lot, and it can have a creep properties very different. So generally, the timber would be a treated timber with so that there is no rotting happens or no pest attacks, which is a dry clean timber. The timber can be 1 year old. As long as it's treated, it's fine. The timber, again, we are talking about a structural timber.
Yeah, the topics how far relevant to Indian conditions. The question, whatever topics you have discussed, so how far they are relevant to India.
The capacity design is completely applicable to India. Steel structures, yes, completely applicable to India. Concrete structures, yes. The timber may not be really applicable, but there are some timber structures even in India, right? May not be really useful for a normal day-to-day practice, but I would say, it may not really applicable, but there would be one job somewhere, where you might have to deal with timber.
Yeah, Ramna sir, are you there? Yeah, the next question, sir. For high-rise structures, we use high-grade materials, which are usually brittle. How can we overcome the brittleness with the ductility?
Oh yeah, that's a very good one actually. If you look into the stress strain concrete of a concrete, so as your grade of concrete increases, your ultimate compression strain is gonna reduce. So what you need to do is you need to detail such that the revised or reduced compression strain doesn't reach. So it's a part of the design.
Yeah. What is the base isolation, sir?
Oh, base isolation is it's like you have a structure. You put rather than directly putting onto your ground, you putting on a rubber pad. Let's say, right? So rubber is so soft, so your structure not gonna deform. Your rubber pad gonna deform. So it's to put it in that way. So what happens is your rubber pad gonna go in a failure, but your structure gonna be very much intact. But so rather than going into really depth, So basically, the idea behind base isolation is you don't transfer the forces because of earthquake or any shaking to your structure, so your structure stays as it is.
Yeah. The next question is, what is the static load for timber structure and what is the deflection for timber?
Static load?
Yeah.
No, load is it doesn't. No, load is a load. It could be dead load. Live load. It's not different to whether it's a timber or concrete. But the limitation generally we limit deflections with a stringent criteria for timber structures because there is a high chance of failure, which is a brittle mode of failure.
Yeah, Shreja sir, closing remarks for this session, sir. Yeah. You can take one more.
Yes.
So one last question by some professor. For high-rise structures, we use high-grade materials, which are usually brittle.
Yes.
How can we overcome its brittle nature with ductility?
So now your concrete is brittle, right? I understand your concrete strain can be increased by providing active confinement. You can't just see concrete as a simple plain concrete. You need to, what you need to do is you need to provide an active confinement so that even the spalling happens outside your cover zone, so your member within the confinement zone is intact.
Yeah, okay. One last question from Pawan.
Pawan sir,
Yep.
I have one question regarding to timber structure.
Yep.
Is there any difference between the stress block for the timber structure as well as the steel?
Oh, no. There is no difference in stress block, but when it comes to timber, you can't go for a plastic design. You go for an allowable stress design.
Okay.
So,
if you give the connection,
yeah.
timber to steel,
Yeah.
already you have shown some pictures. So how can you take the transformation?
So what you need to make sure is, first thing is, in this case, if you have a steel connection and a timber, and say for example again a timber, right? First thing is you need to make sure there is no failure in your timber, right? By providing enough edge distance. Like for example, if you have a steel connection, the edge distance is 1.5 times the bolt diameter, right? So whereas a timber, all of a sudden it goes to 8 times the bolt diameter. So what happens is you are eliminating any kind of failure in a timber element, right? So and then once you eliminate the timber failure, it comes down to standard steel connection design. So if I talk in a capacity design point of view, your weak element is not the timber element, it is the connection.
Yeah.
So still your connection is a ductile, but your brittle element, which is a timber member, which is stronger.
Okay. So ultimately you want to make that thing